Now it is time to start the application of Gauss law on cylindrical symmetry. This is one of the old exam problems. An infinitely long line of a charge, which is this one, carries a uniform charge per unit length. What is this, my son? This is lambda. Okay, let me call it lambda 1. So this is lambda 1. Okay, lambda 1, it is positive. It is distributed uniformly along this line charge. It is given in units of coulomb per meter. The line is surrounded by an infinitely long conducting cylinder, which is this cylinder, shaded one. It is cylindrical shell. Of course, it is very thin, and this is why he is giving us the radius to be 2 centimeter. Okay, so it has only one radius, 2 centimeter. If it is thick, it will give you what is the inner radius and what is the outer radius. So right now it is very thin, and we can consider it to have the radius of 2 centimeter. The shell carries a net linear charge density of -2 10 to the -7 coulomb per meter square. Here, my son, coulomb per meter. You might ask why he gives us lambda for the surface of the cylinder, which is surface. It is not a line. Okay, because we'll see that it will be reduced. Looking from outside, if you look from the outside, due to the symmetry, you can consider the cylinder as being a line, and the line charge density of that line will be negative -2 10 to the -7. Let us call this lambda. This is lambda 2. So in other problems, he might give you sigma, not lambda, for the cylinder. And this is our habit. Sometimes we give you lambda for the cylinder if it will reduce to a line, or sometimes we give you sigma. So there is no problem with this. With the line as the axis of the shell. So this is exactly, the line is exactly at the axis of the cylindrical shell, as shown in the figure. What is the magnitude of the electric field at a distance of 1 centimeter from the line? Okay, so the radius, this distance is 2 centimeters. Okay, the radius is 2 centimeters. He is asking about the electric field at a distance of 1 centimeter. What is the electric field here? Okay, this is part A. Part B, he is asking about the electric field 5 centimeters from the line. So it will be outside, the electric field outside. Let me start with the first part, which is A. To do this, we need to draw a Gaussian surface. And due to cylindrical symmetry in our problem, the Gaussian surface should pass through this point, which is 1 centimeter from the line. Okay, so this is my Gaussian surface. I draw it. It will be a small cylinder. Of course, it is virtual cylinder. It doesn't exist. I put it just in my mind to simplify the calculation of the integration. Okay, we have done this before, but let me do it quickly. The electric field will be, due to the cylindrical symmetry, will be radially inward or outward. Radially outward, because we have positive charge. Lambda 1 is positive. So the electric field is going outward at this point. Okay. And the area, of course, as we said before, will at any point will be in the same direction as the electric field. So the angle between the area vector and the electric field is 0. So cosine 0 will give us 1 all over the curved surface. The electric field, due to symmetry, doesn't have any component other than this radially outward vector, E vector. So Gauss law says integral of E dot dA equals Q enclosed divided by epsilon naught. The electric field is uniform at this surface because at any point on this surface we are at the same distance from the line, so it will have the same value all over, so it is uniform. So we get it out. dA, integral of dA will give us the curved area. So this will be 2 pi r, where this r is 1 centimeter, 2 pi r multiplied by the length, this length, okay? equals how much is the charge enclosed. Charge enclosed inside, if you look inside this Gaussian surface, how much is the charge? We look at the charge from here to there. Okay? It will be lambda 1 multiplied by the length of my Gaussian surface. So this will be lambda 1 multiplied by the length of this Gaussian surface divided by epsilon naught. As you can see, L will cancel with that L, and we are left with the electric field having a magnitude of lambda 1 divided by 2 by epsilon naught lambda 1 divided by R. Okay, and this is nothing but 2k lambda 1 divided by R. This is the magnitude of the electric field. And because lambda 1 is positive, the electric field will be radially outward. Okay, so at any point, the electric field will be coming out. So there, the electric field will be out. Here, it will be coming out, etc. Okay, how much is this if we plug the numbers? It is 2 multiplied by 9, 10 to the power 9, lambda 1, which is 2.5, 10 to the minus 7, divided by R. In this case, it is 1 centimeter. We put it in units of meters. Okay, and this will give you the magnitude, which is 4.5 times 10 to the power 5. The unit for electric field is Newton per coulomb, and the direction is radially outward. Radially outward. Somebody might ask here, is there any effect for the charge lambda 2 on the cylinder which is outside? What is your answer, my son? Of course, Gauss Law tells us that the Q enclosed inside my Gaussian surface will be effective for this symmetry. So my Gaussian surface, this is my Gaussian surface, which goes through the point R equal 1 centimeter. If you look inside my Gaussian surface, you will see only lambda 1. Lambda 2 is outside the Gaussian surface, so it will not affect the net electric field at the point here at 1 centimeter. Okay, its net effect will be equal to 0. Okay, because it is outside. Of course, the electric field for this area, the angle between the area and the electric field will be 0, as we have done before, my son, in the discussion. Okay, let us now answer part B. Part B is asking about the electric field at 5 centimeters from the line, or outside. Okay, let us do it. I can draw a line here to answer B. So part B at R equals 5 centimeters from the line, between brackets, this will be outside the cylindrical shell. Okay, we will apply also Gauss Law, but let me erase this. Now my Gaussian surface should pass through this point. This is my R, okay, in this case, and we know that this is how many centimeters? This is 2 centimeters, okay, so we are outside. This is R equals 5 centimeters, okay. Here we have lambda 1, which is positive. On this surface, we have lambda 2, which is negative. Looking from outside, if you remember, my son, the shell theorem, any sphere, when you look at it from outside, all the charges will act or will affect the electric field as if all the charges are focused at the center of that line. We can extend this to cylindrical symmetry. If you are outside cylindrical symmetry, the cylindrical charge distribution will look like a line of a charge, okay, at the axis of that cylinder. So here, this will be my Gaussian surface. I draw it here. Okay, this is my Gaussian surface. So my Gaussian surface, if you look inside, what is the charge enclosed? It will be lambda 1 multiplied by the length of this line, okay? And we can reduce the cylindrical shell to also another line. So if I draw it here, I can draw the following. Here I have lambda 1 multiplied by this length, and this will reduce, the cylinder will reduce to another line of charges. They should be coincident on top of each other, but I'll draw side by side just to make it clear for us, and this will be lambda 2. And my Gaussian surface goes something like this, okay? And we put it there. This is my Gaussian surface, okay? It has length L, okay? So applying the Gauss law on this Gaussian surface, so E, which will be uniform at any point here, it will be radially outward if the total net charge is positive. It will be radially inward if the net charge is negative. So E dot dA closed integral over this Gaussian surface equals Q enclosed by my Gaussian surface divided by epsilon naught. Okay, what is the area of this guy? We said the electric field is uniform. The area is outward. The electric field is outward because if you add these two, we have more positive than the negative, so it will be radially outward. So E multiplied by the surface area, which is 2 pi r multiplied by the length L, okay, equals Q enclosed. I have lambda 1 multiplied by its length, okay, and lambda 2, but lambda 2 is negative. I'll take its magnitude, and there will be subtraction here. So this will be minus the absolute value of lambda 2 multiplied by the same L divided by epsilon naught. Okay, so L with L with L will cancel, and we end up with the electric field outside equals lambda 1 minus the magnitude of lambda 2 divided by 2 by epsilon naught multiplied by r. But 1 over 2 by epsilon naught is nothing but 2k lambda 1 minus lambda 2 divided by this r. Okay, this is the magnitude of the electric field. Direction, we'll decide about it in 1 minute. So the magnitude, if you do the calculation, this is the magnitude, absolute value. So we'll end up with 2k, which is 2 times k, 9, 10 to the power 9. Lambda 1 minus lambda 2, if you do this, you will get 0.5 times 10 to the minus 7, 10 to the minus 7, divided by r. R in this case is 5 centimeters. We should put it in terms of in units of meters, 0.05 meters. The magnitude will turn out to be 1.8 times 10 to the power 4 Newton per coulomb. Okay? So this is the magnitude. But electric field is a vector quantity. We need to decide about the direction of the electric field. What is the direction of the electric field outside? We have to look at the net charge enclosed in my Gaussian surface. The net charge is positive. Lambda 1 minus lambda 2 gave us positive value. So positive quantity, meaning that it will be radially outward. If it was more negative than the positive, it will be radially inward, because the electric field radiates away from positive charge and sinks in negative charge. Thank you. This is the second example related to cylindrical symmetry. We have a very long uniform line of a charge having a linear charge density 6.8 microcoulomb. It is positive charge density. Lies along the x-axis. It is sitting along the x-axis, y equals 0. A second line of a charge has a linear charge density of, it is negative now, minus 3.4 microcoulomb per meter, and is parallel to the x-axis located at y equal 0.5 meter. We want to find what is the net electric field at a point where y equals 0.25 meter on the y-axis, meaning that it is midway between the two line charges. Let me have a simple diagram for you. This is the positive x, that is the positive y. Okay, the line charge, one of them is along the positive x-axis. It carries linear charge density, let me call it lambda 1. Okay, the other one is located at y equals 0.5 meters. Okay, and it carries lambda 2. Lambda 1 is positive. Okay, lambda 1 is positive 6.8 microcoulomb, while lambda 2 is negative minus 3.4 microcoulomb. And he's asking what is the net microcoulomb per meter, microcoulomb per meter. This y equals 0, this is the x-axis, and he's asking what is the net electric field midway at point y equals 0.25 meter. Okay. We have seen in our discussion, previous videos, that the electric field due to a line charge is given by, let us remind ourselves of this, B due to a line charge equals to, E, the electric field, okay, equals 2K, the electrostatic constant, multiplied by lambda over R at any point R from a line charge. We have done this before, so there is no need to derive it again. By the way, you don't need to worry about this, my son. It is given in the formula sheet. All what you need to do is to recognize this formula. This is the formula used to find the electric field at a distance R from a line charge distribution. Okay? And the direction of this electric field will be outward if lambda is positive, and it will be inward if lambda is negative. Okay, so at this point here, this is a positive, okay, charge. So the electric field due to this lambda 1 will be in which direction? Outward. So it will be in this direction. Let me call it E1. So E1 is radially upward at this point, okay? What about lambda 2? Lambda 2 will produce electric field sinking in or going toward lambda 2. Okay, so E2 will be in this same direction. Okay, how much is E1 and E2? Here we can write that E1 can be written as 2K lambda 1 divided by how far you are from lambda 1, which is 0.25 meter. In which direction? It is along the positive y-axis or positive j. Okay, E2 will be how much? It will be 2K, but now to be lambda 2 divided by 0.25. How far is this point from the line charge? This is 0.5, this is 0.25, so the distance from here to there is 0.25. Okay, and of course here I'll take only the magnitude of lambda 2. Why? Because I consider the direction here. It will be moving toward, the electric field is directed toward the line charge number 2. So this is the direction. You don't need to consider the minus sign here. Okay? So the net, E net at that point will be equal to E1 plus E2. E1 plus E2, this is the superposition principle, and this will be 2K divided by 0.25 multiplied by lambda 1 plus lambda 2, and this will give us the magnitude. So this will be 2 times 9, 10 to the power 9 divided by 0.25 multiplied by lambda 1. Lambda 1 is 6.8, 10 to the minus 6 plus the magnitude of lambda 2, which is 3.4 times 10 to the minus 6. If you do this calculation correctly, this will give you the electric field, which is 7.3 times 10 to the power 5 Newton per coulomb. And the direction, if you want to write it in vector format, it will be in the positive y direction. We are done with this problem. But what will happen if he asks us at different points? Here, he asked us to find the net electric field at midpoint between lambda 1 and lambda 2. Let us extend our understanding. We are done. Plus, this is the answer of the question. Let us have other situations. If he asks us to find what is the net electric field at a point, let me call this point here. This is point B. What will be the net electric field? Okay, this is positive charge, so the electric field E1 will be in this direction, E1. Okay, that one is a negative charge. Okay, so the electric field will be going toward it. Okay, this will be E2. So the net will be 0. Allahu A'lam. You need to calculate how much is 2k lambda 1 over r, and this will be small r. Okay, then the electric field E2 will be 2k lambda 2 over r, and this r will be that much distance. So not necessarily these will cancel each other. It will depend on the values of r and lambda 1 and lambda 2. Okay. If you want to find what is the electric field at this point, for example, these are extra points. Here, E1 will be outward, so it will be this way, E1, because lambda 1 is positive, electric field is going out of it. E2 will be toward this line, it will be large because we are close to it. So this is E2. Okay, so the net electric field will be the difference between the two. The net will be the difference, but here the net electric field was the summation because they are in the same direction. As a final advice, my son, I encourage everybody to go and solve as many problems as you can, because the more you practice, the more you understand, and the more you excel in the exam. With my best wishes, and see you in future videos, inshallah. Assalamu alaikum.